Hello. What we want to talk about now is a bit of coordinate geometry. Much of computer vision is based around geometric ideas, and we're not going to go into the depths of it, but we are going to sort of hit the surface of it, particularly in the area of coordinate systems. These are effectively the foundational geometric keys that we need for quite a lot of the computer vision activity, certainly the ones that we'll do in this course, but quite a lot of the ones that anyone would be doing if you're working with images. So the place to start really is with coordinate systems, and normally when you think about your images you'll think about a coordinate system, but here we're going to need multiple coordinate systems, and that's going to include the object and scene coordinate systems as well as the image coordinate system. If you have multiple coordinate systems, you need to have ways to relate those coordinate systems together. And that's where we're going to talk about coordinate system transformations. Most of you are used to rotations and translations, but when you're looking at complicated sets of coordinate systems, it can be a bit messy working with all of the different individual transformations. So we're going to look at a technique called homogeneous coordinates. We're not going to go into the full-blown version of homogeneous coordinates, but we're going to look at how we can pack the rotations and translations together. And then finally, with all those tools, we can look at how we can deal with multiple reference frame transformations. Okay, let's get started. Well, we're going to end up with trying to recognize some objects. So they're going to be in different places in the image. When we want to recognize them, we're going to need to have some kind of a model of the object. So we're going to need to have a way of describing the object. So here's a description. Well, how are we going to relate this description to this different place of the object in the image? So we're going to need a way to represent all these things. We need a way to represent the object features. We'll be talking more about that later. We're going to want to have a way of describing those objects in a way that's independent of the image object's position. So we don't want to have a different description for this image and this image and this image. And we're also going to want to have a way of talking about where this object is inside these images. That's sort of like saying, where is it? Okay, so we need some descriptions right here, and that's what all the coordinate system stuff is going to be about, is putting all those pieces together. We want to have general models. Okay, here's our, let's say, our general coordinates. Here I've taken the coordinate system in the upper left-hand corner. That's typically where images start their coordinate system origin, and we want to be able to describe that object, so we're going to have some sort of generic type description. It's going to be aligned usually with some sort of relative to the coordinate axes, because that's convenient for us to do the modeling. But on the other hand, we're going to want to also have some sort of specific coordinate systems where we're talking about where the object is in the scene, because the objects can move around inside the scene. We're going to want to talk about a more generic one when we talk about the image. That's going to have its coordinate system origin up here, just in the same way as we did the modeling, something generic. So we're going to have a mixture of things, both specific and generic, and we're going to want to have ways to talk about how one relates to the other. Right, okay, where do we start? Well, we're going to start by having separate coordinate systems. We're going to have multiple coordinate systems, and then we're going to have to link them by some sort of reference frame transformations. We'll get on to the reference frame transformation bit in just a minute. But let's start with the image coordinate system. Well, like I said, we have it up here, starting at the upper left. We've got a certain number of columns and rows in the image. Here's the number of columns, R is the number of rows. That gives our image. Okay, and then we could talk about points using our sort of standard coordinate geometry, using the coordinates of that point. We're going to have to sort of relate these different coordinates, assuming that everything is aligned to begin with. Our first problem is when we measure the objects or we make our models, they're going to be measured in some kind of scene units, like millimeters, for example. When we measure something in the image, we're going to have something measured in terms of pixels. We're going to need a way of relating the two together. Fortunately, most image sensors have a static kind of relationship between the scene and the image position, especially if the camera is rigid. There are some complexities that we're not going to talk about here, but let's assume that we have a rigid camera. Therefore, there's just going to be some kind of a scale factor which relates the image coordinate scale to somehow the scene coordinate scale. Well, let's talk about our objects. We want to talk about where our objects are in the image. So here's our object. In this case, it's just a simple little box. It's got its coordinate system. So we can see right here, its little origin of the coordinate system, its column and row position. Here's our image or our scene, something like that. It's got its own little coordinate system. And we want to be able to relate the two together. We'll talk about how to do that. There may also be some sort of like camera coordinate system where the camera is based in the scene. There may be also a variety of other coordinate systems, robot coordinate systems, or image coordinate systems. We'll be talking about how we can represent all of these together. Well, let's look at see how we can place the two coordinate systems relative to each other. This is where we go into the idea of a coordinate system transformation. We're going to look at this in several different ways. In order to talk about where one coordinate system is relative to another, we use the transformation. And in 2 dimensions, we really need to specify 2 things. What is the orientation or the rotation of one coordinate system relative to the other? And we're also going to need to talk about the translation, the position of the object relative to the other. Okay, so it turns out in 2 dimensions, we need one rotation parameter. That's the rotation of the object around in the image. And the second is the translation, which needs 2 parameters, which tells about how far that object is moved either horizontally or vertically. So in 2 dimensions, that's all you need. When we get to 3 dimensions, we'll extend this a little bit more. But for now, we're just going to do it in 2 dimensions. When we talk about math, typically we're going to have vectors which are column vectors, sort of going up and down, but it's a little bit hard to write on the slide sometimes, and so we might use the transpose thing, which turns a row vector into a column vector, or vice versa. So that's a little bit of our notation. Right, okay, so now we've got a lot of the building blocks already for the simple coordinate system transformation. Imagine that we have our point here, P, to begin with, and we want to move it. Well, that's just simple vector geometry. If its point is right here, and here is our translation vector t, then that's where the point ends up. Well, we can express that algebraically, and that's what we're going to need to do any of our computations. And so that's why we start with our point originally. Let's start here at AB, and we have our transformation that's given by this. And when we talk about our transformed or translated point, we just add the vectors together, the position plus the vector. That gives the new position right here, and that's the coordinates of that point. Kind of assuming that you've already done all of this. This is kind of high school level geometry, but maybe you haven't done it for a while, so we'll have a little bit of a review. The more complicated bit is the rotation. So if this is going to be our rotation angle theta, we're going to represent our rotation in terms of a matrix. This is the matrix that we use, call it a rotation matrix. The values in that matrix are given by here, the cosine and sine. It's a little bit tricky to remember all of the position of all these numbers, but the thing maybe too easy to remember is that the cosines are always on the main diagonal, and the sines are off the main diagonal. And one of those signs is going to have a minus sign in front of it. Sometimes you might see the minus sign down here or there. That's largely a matter of convention. Sometimes people say this theta is related to a rotation that's clockwise in the image. Some people will say this theta is related to an anti-clockwise or counterclockwise rotation in the image. And if you change the convention, then you've got to move that sign, the minus sign, around from here to there. So whenever you're working, be sure to find out what convention you're working with. Right, so with that, now we want to talk about a rotation of our coordinate system. So here's our original point, P. It's in this particular position. We want to rotate that by an angle theta. Okay, and here we're going to choose our theta as a positive clockwise rotation around the coordinate system. So our positive angle here goes down there. Here's our point P, and here's our rotated point down here. And that's where our matrix notation comes in. Originally, we have our point P here. We use the rotation matrix that we saw on the previous slide, and we can talk about the position of the object. The rotated position is just by RP. We could also do this algebraically and expand it out, but as you can see here, it's a little bit messier. Okay, this is a much more compact type notation to actually encode that rotation, but these two are equivalent, and sometimes you do need to work with all the extra details. So now we want to put it together to make a complete transformation. We've got our translations, which move things around in the image. We've got our rotations, which orient the things around. And the way we're going to put it together is use this particular form. So if our original point here is a P, we say, starting up here at the orientation, we rotate it downwards by theta, and then we translate it down by t, our translation t. Okay, so now we have a way of talking about where this object is in the image. We can say this object is right here. It's parameterized or described by this t translation vector and this theta, this rotation vector. So we have a vocabulary for talking about where things are in the image. Or this could be the scene, or this could be some of the other coordinate system. We have a way of talking about things in the coordinate system now. There is a kind of convention that we're going to stick with. We're always going to do the rotation first and then do the translation. You can do the geometry in a different way. You can apply the transformation first and then the rotation. But the understanding of what's happening here is just not quite as easy for the computer vision case. And so that's why we do the rotation first and then we do the translation. If we did the translation in a different order, we wouldn't use the same values for the translation there, so be careful about that. Right, well, we're going to move on to a more complicated problem, and that is, what do you do when you have multiple representations, multiple different transformations? It can be a bit complicated dealing with all of these individual and rotations and translations. We'll see an example of that just coming up in a minute. In order to make that simpler, we're going to use a representation called homogeneous coordinates. When we did the transformation a minute ago, we had to do two operations. We had to do a multiplication by the rotation matrix, and then we had to add the translation vector on afterwards. Okay, so that was actually two different things, and somehow it's more conceptually easy just to think about a simple single transformation. So that's where we're going to use the homogeneous coordinates for, at least here. In order to do that, we're going to have to take our original points and we're going to have to extend them. So originally this point P was at coordinate position AB, and we're going to have to extend it by sticking a constant 1 here at the end. So it's now a 3 vector rather than a 2 vector. We're going to have to take our vectors, that's like our translation vector, and we're going to have to extend that as well too. In this case, for the vectors, we're going to have to extend it by adding a 0. And then finally, we're going to pack together our rotation and our translation into a single matrix. So here, now we're going to end up with a 3 by 3 matrix. You can see the rotation matrix is here in the upper left. Okay, the translation is here, and we're going to pack in some other constants down here, zeros and ones. And the net result is, instead of having to do our rotation first and then our translation in order to move our point P around, we can do this just with a single transformation using our new 3 by 3 T matrix by transforming just this point. But remember, we've extended that point a little bit. Now this is not the full-blown version of homogeneous coordinates, and we're going to come back to that a little bit later when we're looking at the stereo. We're going to look at projective geometry. This is just kind of the simplest version of it, and it can become very complicated. And we're not going to go to the full complexity, but we will extend this a little bit more. Well, what can we do with this? Well, imagine you're going to deal with a robot. Okay, so here's a picture of a little robot. It's got different joints, it's got elbows, it's got wrists, it's got shoulders. And each one of these movements represent a reference frame transformation. If I want to talk about where my wrist is, well, I need to consider the transformation here at the wrist. I need to consider the transformation here at my elbow. I need to consider the transformation here at the shoulder, maybe at my waist. Maybe I move around as well too. Maybe the robot's a mobile robot. Each of these reference frame transformations adds its own complexity, a bit like what we've seen just a minute ago. What we would like to be able to say is, well, where is the position of some point relative to all the bits of the robot when the robot is moving around? Well, here I've sort of specified just a very simple kind of robot where I've got two joints. We've got a fixed, sort of upper joint right here, shoulder joint. We've got an elbow joint, something like that right down here, and we've got a wrist joint down here, and maybe we're looking to specify the position of some little object like my little clicker here relative to my shoulder joint, which itself is maybe based relative to some sort of world coordinates, okay, because my robot is here relative to where the world is. So you can imagine there's a bit of complication here with all of these different reference frame transformations. A transformation from the origin to here, there's a transformation from here to there, there's a transformation from here to there, and another one from here to there. And there's actually some joints in here, so there's some variables as well. We could express all of this in a kind of normal sort of school-based geometry method, but it can be very complicated with all these different transformations. And so that's why it's great to use the homogeneous coordinate representation, where we can pack the whole transformation just into a single matrix. And that's what we're going to do. So here's our transformation for the wrist joint. Here's our transformation for the lower arm. There's going to be a transformation that gets from the origin down to the robot itself. So if I want to talk about where something is, I can say, well, if this point is relative to the tip of the robot, I'm going to start here. Then I can go say, well, where is it relative to the wrist? Where is it relative to the lower arm? Where is it relative to the robot as a whole? And that tells me something about where that point is in the world. And we just do this by multiplying all of these matrices together. That's a whole lot easier than the individual rotation and translation. These transformation matrices are invertible. That means we can go backwards as well. So if I know where something is in the world, I can try to go backwards to figure out where it is relative to the robot. Because each of these matrices is invertible. I can just sort of invert, get the T0 over here, get the TL over here, get the TW over here, and that gives me my X. Okay, so that gives me the coordinates of our scene point. So that gives us a little bit of a review of the technology that we're going to use throughout the course, particularly in the first lecture and then later when we're doing the stereotype calculation. But we'll see little bits and pieces of this geometry as we go all along. It's also given us a little bit of an introduction to the homogeneous coordinates, and as I say, when we get to the stereo, we'll be doing a bit more of that as well too. We'll be extending it into the world of projective geometry a bit from just the simple extension that we've got right here. Anyway, thank you very much.